Alright, so section 10.6, calculus or polar curves. So now it's basically bringing on the calculus. Section 10.5 was completely all review. It doesn't mean that you don't need to know this review for section 10.6. Alright, so a few things. Slope of the polar equation. So to find the slope of a tangent line to the polar graph, knowing that r equals f of theta, we use the two polar equations. So you change x to r cosine of theta, y becomes r sine of theta, and the product rule. Okay, so the slope, which is dy dx, is going to be the derivative of y over the derivative of x. And to find the derivative of y, we're going to need to use the product rule. So the derivative, so basically the first guy times the derivative of the second guy plus the second guy times the derivative of the first guy. And you do the same thing at the bottom. Clean this up if you have to, if the equation allows it. And remember that the denominator cannot be 0. Or you can create y of theta and x of theta first, and then find the derivative of each individual one. So the curve r equals theta has, and this is the same for parametric, it has a horizontal tangent when dy d theta is 0, okay, which makes sense. So basically if you have a curve like this, your horizontal tangents are going to be right there and right there. So basically your lines are horizontal, so your y equals, right? The line is a y equals line, so that's why your slope here is 0. And then dx d theta cannot be 0. And then you have the vertical tangent at the point where, so for example right here, you can have a vertical tangent line where dx d theta is 0. So just think about it like the actual lines. So you have a vertical line when x equals 0, when x equals something, and then the horizontal is y. If both derivatives are 0, so if both of them end up being 0, that cannot be the case. So no conclusions can be drawn without further investigation, and we'll talk about it when it comes up in an example. Okay? All right, so the first example is it's number 9 from page 566. Find equations for the horizontal and vertical tangent lines. Horizontal and vertical tangent lines, so the curve given by r equals -1 plus sine of theta from 0 to 2 pi. Make sure that you're always aware that it cannot be 0 over 0. Alright, let me just tell you right now, I did not give you enough room to do this problem. Okay, so I'll start the problem, and then I'm going to be using post-it notes. Okay, one sec. Alright, so the first thing that we need to start off is we know that x is going to be equal to r cosine of theta, correct? And here r is -1 plus sine of theta, so it's -1 plus sine of theta is my r times cosine of theta. And I'm just using these two equations. X equals r cosine of theta and y equals r sine of theta. And we know what r is based on our parametric equation. And then my y, I'm just going to do it right next to it. My y is going to be -1 plus sine of theta, which is r, times sine of theta. Now putting these in parentheses doesn't really matter, but for notation's sake, I guess. Alright, so since we're finding equations for horizontal and vertical tangents, we have to, of course, find the derivative of x, and we have to find the derivative of y. And the way that we're going to find the derivative of this equation of x is we're going to use the product rule. So what I like to do is take the first guy, derivative of the second. It doesn't really matter the order since it is going to be added anyways. So it's -1 plus sine of theta times the derivative of the second guy, which is negative sine of theta, plus the second guy times the derivative of the first guy. And the derivative of -1 is 0, and the derivative of sine is cosine. I'm just going to put a separation right there. So now when we clean this up, first off, this gets distributed. So we have -1 times negative sine of theta, which is sine of theta, plus, or sorry, minus, because that's a positive and that's a negative, sine squared of theta, plus cosine squared of theta. So this is our dx d theta. We're going to do the same thing for dy d theta. So the first guy times the derivative of the second guy plus the second guy times the derivative of the first guy. And we clean this up. And we're going to get negative cosine of theta plus sine theta, cosine theta, plus sine theta, cosine theta, which you can see that these two can be combined as 2 sine theta, cosine thetas, minus cosine theta. And really, you notice that both of these terms have a cosine theta, so you definitely want to simplify it because just it makes it easier when you're setting one of the derivatives equal to 0. You'll see what I mean when we do this. So you notice that you have a common factor between these two, so I'm going to take out a cosine theta, and I'm left with 2 sine theta minus 1. So this is my dy d theta. And see here, I didn't do that because I don't have a common term between all three of these parts. Alright, so now it brings us to actually finding the horizontal. So right now I'm going to work on the horizontal first. So what did the definition say? The definition said that we have a horizontal tangent when dy, when the slope is 0. And how do we get dy, the slope being 0? That means the top. So basically when dy dx is 0. And we get dy dx to be 0 by allowing dy d theta, which is the top part, is going to be 0. Right? And then the dx d theta has to be a number. So we definitely have to check this. So it's going to be 0 over some number for it to be 0. So that means the top part has to be 0. The bottom cannot be 0. So dx d theta can't be 0, but this guy is 0. So since we've already solved for dy d theta, dy d theta was right there. Cosine of theta times 2 sine minus 1. We can set it equal to 0. And this is why it makes a lot more sense to factor it here, because look at this. If we know that this is set equal to 0, then we can use the product property and basically say, alright, then this guy can be set equal to 0, or this guy is equal to 0. So I'm just going to continue here. This is why I'm telling you I did not give you guys enough space. So where is cosine of theta 0? It's basically 0 at pi over 2 and at 3 pi over 2. Okay, and then I forgot my thetas right there. And then for the second part, when you solve this out, this becomes sine of theta equals add 1 divide by 2, so that's sine of theta equals 1/2. Where is sine of theta 1/2? And that happens at pi over 2, right, where the y is 1/2, and at 5 pi over 6. And remember, we're staying in between 0 to 2 pi, so that's why I'm going all the way around the unit circle for these. Now we're not done, because remember that to find the horizontal tangent, yes, dy has to be 0, but remember that dx cannot be 0. So we have to make sure that our dx d theta is a number. So we're going to check. Okay, so here I'm going to check each 0. So dx d theta is not 0, because if it is 0, then there's other stuff to do that we don't know about yet. Now, what that means, I'm basically going to take my thetas and I'm going to plug them in to my dx d theta, and I'm going to make sure that it's not 0. So if I plug in my theta into pi over 2, pi over 2 into theta over here, we're going to get sine of pi over 2. I guess I'll do it for the first one, but I'm not going to do it for all of them. I'll just give you the answers for the rest of them. So sine of pi over 2 is going to be 1 minus sine of pi over 2 squared, which is just going to be minus 1, plus cosine of pi over 2, which is 0. So here, what do you notice? What do we get? 1 minus 1 is 0, plus 0 is 0. So guess what this tells us? That if theta is pi over 2, dx d theta is 0, so that means that cannot be one of my horizontal tangents. So I'm going to go ahead and check the rest of these guys. So 3 pi over 2, you plug this in, and you actually end up getting -2 once you plug that in. So that works. Check the next theta. Oh, and you did say, sorry, and I don't know why I put pi over 2. This should have been pi over 6 right here. So I'm going to check pi over 6. And pi over 6 gives us a number. It's not 0. Okay, very ugly number. But you really don't need to find out exactly what number it is as long as it's not 0. So that checks out, and then the last one is 5 pi over 6, and that actually gives us a number as well, so that checks out. Alright, so now we have our 3 thetas. Boom, boom, boom. We're not done. So now that we have our 3 thetas, we want to find our horizontal tangents. So basically, our horizontal tangents have the equation of y equals r sine theta. And if in this particular case, our r is -1 plus sine theta times sine theta, right? Because our horizontal tangents deals with the y. And they occur at 3 different thetas, at theta equals 3 pi over 2, pi over 6, and 5 pi over 6. Agree? So this is where my post-its come in. So I have 3 different thetas. I don't need this much space. Okay, I'm just being dramatic with 3 different post-its because we have 3 different thetas. So my first horizontal tangent is when at y equals theta is 3 pi over 2. So I'm going to use that equation. I'm going to plug in -1 plus sine of 3 pi over 2 times sine of 3 pi over 2. Solve this, and you get your first horizontal equation. So we got -1 minus 1 times -1, which is 2. So my first equation is y equals 2. So I have a horizontal tangent at y equals 2. Next one, second, is y equals when theta is pi over 6. So same thing. I'm going to plug in -1 plus sine pi over 6 times sine pi over 6. And once you do that math, you get -1 plus 1/2 times 1/2, which is 1/2 times 1/2, and that is 1/4. So my second horizontal tangent is at y equals 4. And my third one is at y equals theta is 5 pi over 6. So we're going to plug that in into -1 plus sine 5 pi over 6 times sine 5 pi over 6. And we get y equals -1/4. So my 3 horizontal tangent lines are at y equals 2, y equals 4, and y equals -1/4. And now, after you've gotten those 3 do the same for the vertical tangents using dx d theta equals 0 and making sure that dy d theta does not equal 0, and it's the same process. You do this. Alright, remove my post-it notes out of the way for example 2. So, example 2 says find dy dx. So find the slope and find dy dx and the slope of the graph of the polar curve at the given value of theta. So here's r equals 2 plus 2 sine of theta, and they want us to find the slope at this point right there, at pi over 2. So really quick, let's just do a recall. What kind of graph is that? You have to be able to spot these. So this is a cardioid. And remember, the cardioid, it's reflected over the y, so it's going to be a heart going up and down. And the biggest radius is 4, so 1, 2, 3, 4. And the smallest is going to be 2 minus 2, which is 0, and that tells us that it's a cardioid. So it's going to go out like this, and this is going to be the 2. And then it's going to come back around, kind of like that. It's not perfect, pretty close. So looking at the graph, what they want us to do is they said find dy dx and the slope of the graph at pi over 2. So here's pi over 2, correct? What is the slope at pi over 2? So here's theta is pi over 2, and you notice that the slope of this line, it's a horizontal tangent. So the slope is 0, which means dy d theta is 0. Okay? So if you graph this really quick, then you basically know the answer. Okay, you know what the slope is. But the first part does say find dy dx and then actually show the work. So right now what we're going to do is we're going to prove what we just saw right here, that at pi over 2 the slope is 0, which means that there is a horizontal tangent at pi over 2. So our two parts are x equals r cosine of theta and y equals r sine of theta, right? Because to find dy dx we need to separate, find the derivatives of each, and then put them together. So x equals 2 plus 2 sine of theta times cosine of theta, and y equals 2 plus 2 sine of theta times sine of theta. So when you find the derivative, dx d theta, you use the product rule. So 2 plus 2 sine of theta, the first guy, times the derivative of the second guy, plus the second guy times the derivative of the first guy, which is going to be 2 cosine theta. Clean this up. So we get negative 2 sine theta minus 2 sine squared theta plus 2 cosine squared theta. No factors in common, so I'm just going to leave it like this. Alright, same thing on this side. We're going to find dy d theta. And we end up with 2 cosine theta plus 4 sine theta cosine theta. So therefore dy dx, okay, is going to be 2 cosine theta plus 4 sine theta. I probably should have factored out a cosine here. Yeah, let's do that. It may help us, it may not, but let's just do it just for sake of staying consistent. So we take out a 2 cosine theta and we're left with, and we can take out a 2 too. So this is 1 plus 2 sine theta. So let's see if it's going to help us. I'm going to leave it here, but I'm going to write in exactly what I had going right here. Sine theta, cosine theta, and all of that is over dx d theta So the question is, what is dy dx at theta equals pi over 2? So I'm going to take theta, pi over 2, and plug it in here, and you basically get cosine of pi over 2 is going to be 0, so 2 times 0 is 0, plus 4 times 1 times 0, which is 0. And then down here, negative 2 times sine of pi over 2, which is negative 2 times 1. And then you get negative 2 minus 1 squared times negative 2 minus 2 plus 2 cosine squared of theta, which is 0. So you end up with 0 over negative 4, which is 0. So this was verification, okay? it tells us that the slope at this point right here is 0. And the reason why it's 0 is because dy d theta was 0, but dx d theta was a number. Alright, I'm going to make a part 2 to this video, just because we're already at 25 minutes here.